Today I am going to talk about buckling of columns. What is this and why do we pay particular attention to a long column? Let's figure out. Buckling is a phenomenon under which a column can suddenly fail due to excessive compressive load. The buckling in a column depends on the elastic stiffness of the material rather than its load-bearing compressive strength. That's why the buckling load requires a separate consideration in the design and the stresses, as the failure due to buckling could occur before the stresses in the column satisfy the yield criterion. The buckling induces instabilities in the structure, causing it to fail. The buckling can be due to flexural or torsional loads and is categorized as flexural and torsional buckling. There is also a mixed case in which the combination of flexural and torsional load causes the structure to buckle, known as flexural torsional buckling. Buckling may occur at stress values lower than the yield stress, and it is a function of material stiffness and slenderness rather than strength. The load at which a column begins to buckle is the critical buckling load. Today we are going to find out the critical buckling load for the column with the following properties. But first, I'd like to start with a description of the procedure for solving this problem. First, you have to calculate the slenderness ratio and compare it with the critical slenderness ratio. The point of calculating the slenderness ratio is to figure out which equation we must use to calculate the critical buckling load. If the slenderness ratio is lesser than its critical counterpart, we classify the column as a short column. The short columns are more prone to fail due to compression and without much buckling. Suppose the slenderness ratio is larger than the critical slenderness ratio. In that case, the column is considered a long one, and you must use Euler's column buckling equation to calculate the critical buckling load for the column. If the slenderness ratio is lesser than the critical slenderness ratio, but larger than its critical counterpart, you must use Jasinski's column buckling equation. Let's summarize. Having solved the slenderness ratio and chosen the appropriate formula, the next step is to calculate the critical buckling load. The slenderness ratio is a simple terms is a means to define the aspect ratio of a column or a building. It is the ratio of the effective length of the column and the least radius of gyration. We have already known the length of the column. That's why the next step is to find the radius of gyration and the factor accounting for end conditions. What have you known about the radius of gyration? The radius of gyration is the square root of the ratio of an area moment of inertia and cross-section area. This is the main formula. Let's determine the area of cross-section and the area moment of inertia. Next, divide the area moment of inertia to an area of cross-section. And finally, determine a square root. Having solved the radius of gyration, the next step is to find the factor accounting for end conditions. Effective length factor, or factor accounting for the end conditions, is obtained using the boundary conditions applied to the column. Each boundary condition has different restrictions on the associated degrees of freedom at the top and bottom end of the column. The table below mentions the value of the effective length factor. The end of a column can have one of three support conditions. It can be pinned, free to rotate, by prevented from sliding sideways. It can be fixed, like the wall end of a cantilever beam, prevented from rotation or sliding. It can be free to rotate and slide, like the free end of a cantilever beam. If both ends are pinned, the column bows in an arc equal to the length of the column. The effective length of the column is its own length. If both ends are fixed, then the column cannot rotate at its ends. It bows in the center relative to two inflection points located length divide to 4 from each end, so the effective length of the bow is half the column length. If the end is fixed while the other is pinned, then the column can rotate about the pinned connection. In our problem, we have a column pivoted in both ends. That's why the effective length factor is 1. Let's calculate the slenderness ratio and move on to the choosing appropriate formula for critical load. The critical slenderness ratio and the critical counterpart you have to find in a table and compare with our slenderness ratio. In our problem, we have the slenderness ratio, which is larger than the critical slenderness ratio. If you know, in that case, the column is considered a long one, and you must use Euler's column buckling equation to calculate the critical buckling load for our column. If you see on this formula, you will notice that we have already had all elements for finding the critical load. Let's do this. What else should we do? You know, Euler's equations help us find the load and stress when buckling first starts, assuming perfect loading conditions and materials. In real life, we need to include a factor of safety. Let's calculate this factor. For this, we must divide the critical load by given load, and the result must range before 1.8 to 3. our factor of safety is 1.9. That's why the stability condition is fulfilled. This is last but not least. I am going to look at some information which is also very important. If you look at the formula, stress in the column, you will find some factor, phi. What is this? Phi is reduction factor of a lovable compressive stress. We have already calculated the slenderness ratio. That's why with the following table you can find the reduction factor of a lovable compressive stress by interpolation. Some machine design problems start with a known load and column length, and your job is to calculate the minimum diameter of a solid round rod to allow the column to survive buckling. Or you have to choose the appropriate cross-section area. In this case, remember that you have to rewrite the formula of the allowable stress, and you have to use a reduction factor of allowable compressive stress. In conclusion, you can see that when we talk about column buckling, we have several ways to solve this problem, and our choice of formula depends on the material stiffness and slenderness. If you found this video useful, don't forget to give it likes and subscribe to my channel. Thank you for your attention. Happy practicing!